In this video, we now complete our look at solving these second order wholies by discovering what do we need to do if our auxiliary equation has complex roots, right? And so what we could do is we could actually, like do a particular example and then work with specific numbers. But I think this is actually one of the cases where we can do it slightly more generally, right? Now, suppose the auxiliary equation of, again, I remember what we're solving, these differential equations that look like this, right? So suppose the auxiliary equation of this differential equation, which is am squared plus bm plus c equals 0, has roots of the form m equals, and I'm going to use alpha plus beta I, so that would be your m1, or m2 alpha plus or minus beta I, right? So suppose our roots end up being of this form, right? Where alpha and beta are real numbers, but I is our imaginary unit, right? So where alpha and beta are real numbers, and then I is the square root of -1. So what do we do in this case, right? Well, let's see what it says. I mean, if we follow our pattern of the two previous cases, right, where we had real distinct roots or real repeated roots, we would say that y1 is equal to, and it would be this number, it would be e to the alpha plus beta I times x, right? And then we would do the same thing for y2. We would say that y2 would be e to the alpha minus beta I times x, right? We would take whatever the solution is, and here we got two solutions, and these are called complex conjugates, right? But the thing is, it would be nice if we could get solutions, right? Since these are functions of a real variable, we would like to get a solution that doesn't involve I, right? So what we're going to do here is a bit of algebra, and we're going to use Euler's identity to rewrite this and see, and do the same thing for this one, and see if there's anything that kind of jumps out at us, right? So let's take both of these and rewrite them. So the first thing I will do is I'll distribute the x. So I'll have e to the alpha x plus, and then I'll say beta xi, so I'll put that right there. Then let's go ahead and factor this e. So I can write this as e to the alpha x times e to the beta xi. And then I'm going to use Euler's identity on the second e right here, because that's the one that has the imaginary unit I. So I'll keep writing the e to the alpha x, and then applying Euler's identity now, this becomes cosine of beta x plus I sine of beta x. All right? Okay, so that's not too bad. We still have the I in there, but at least we see some familiar functions. We see our exponential function, and we see our cosine and sine together, and this is due to Euler's identity. If we do the same thing here, the only thing that's different is that there's a negative in front of the beta, right? So for instance, I can look at this and just write down e to the alpha x, and then I can write it as plus negative beta xi, right? Just, again, wherever there's a beta, just put a negative in front of it, because that's the only difference between these two roots, right? The coefficient of I here is beta. The coefficient of I here is negative beta. So this will be e to the alpha x, and then times e to the negative beta xi. And then again, you applying Euler's result, so I'm going to end up with e to the alpha x, and then in parentheses I'm going to have cosine of negative beta x plus I sine of negative beta x. Right? Very, very similar. But now here, this I can take it a step further because I have some fundamental properties of sine and cosine. I know that cosine is an even function, and I know that sine is an odd function. So since cosine is an even function, well, what does it mean? It means the cosine of negative theta is the same as the cosine of theta. So that's for all theta. And similarly, since sine is odd, the sine of negative theta is negative the sine of theta. So I can use the even and odd identities for cosine and sine respectively and write this down slightly more simplified. So this becomes e to the alpha x, and then in parentheses, well, I can get rid of this negative sign because of this is the even property of cosine. So I still end up with cosine of beta x, and then this negative, excuse me, that's in front of the beta. Here I can bring it in front and change this plus sign and make it a minus I sine of beta x, right? So there we go. So if we end up with complex roots, we will end up with one function that looks like this and another function that looks like this. But what if I apply the superposition principle, right? So what if I do this? So by the superposition principle, then every solution must be a linear combination of these two. So then y would have to be c1 times this. So let me write it. So c times y1, c1 times y1 plus c2 times y2. Well, let's write that down and see what we can get out of this. Fix my c here. So c1, and then times all of this, so I have my e to the alpha x, and then in parentheses I have my cosine of beta x plus I sine of beta x, and then do c2 times this, so plus c2 times e to the alpha x, and then in parentheses I have cosine of beta x minus I sine of beta x. Well, what do we have in common? We have e to the alpha x in common, so I'm going to factor that out. So we'll have e to the alpha x. And then what's left? Here I have c1 times this cosine, and then plus c2 times this cosine. So I'm going to write it like this. So I'll have c1 plus c2 times the cosine of beta x. And then what do we have in terms of the sine terms? So I have my I, and then I have c1 times this, and then c2 times negative sine. So I can write it like this. So then this will be c1 minus c2 times and sine of beta x. But if you notice, this is just another constant. So this, I can just label it as K1. It's another constant. The I is a constant. It's my imaginary unit. So this entire coefficient here is a constant. I can just call it K2. So what do I end up with? So I end up with my general solution, which is e to the alpha x times some constant times my cosine function plus another constant times my sine function. So then, if I kind of do the reverse now and distribute my e, so one last thing I'm going to write is now this. If I distribute the e to the alpha x, I'll have this. I'll have k1 e to the alpha x times the cosine of beta x plus k2 times e to the alpha x times the sine of beta x. Now what do I have here now? I can see the linear combination of these two functions. So one function here would be this. This would be like my y1, right? And this here would be my y2. So it's not until I actually apply the superposition principle and the expressions that we derived above can I identify now that in the case where I have these complex conjugate roots, I can identify this as one function and this as a linearly independent function. Both of these functions are solutions to my original differential equation, right? And this is how we can end up, even in the case of complex roots, we can still end up with real functions that satisfy the differential equation. Really, really remarkable. So let's state this in the form of a theorem, right? And it basically says this. So if, or for our second order whole e like this. Now, what would lead us to the complex case, right? Well, again, that discriminant will tell us everything. What leads us to the complex case is if we end up with a negative number under the square root. So if our b squared minus 4ac is less than 0, so if the discriminant is less than 0, then the roots or solutions of our auxiliary equation must be of this form. So it must be of the form m equals, and then I'll write it as plus or minus, so it's going to be alpha plus or minus beta I. And that's why we refer to these as complex conjugates, because they occur in pairs, right? One's a plus, one's a minus. It must be of this form. Moreover, a basis for the solution set of the differential equation. So moreover, y1 equals, so here's the first function, e to the alpha x cosine of beta x, and y2 equals e to the alpha x sine of beta x. These two functions now form a basis for the general solution, right? So form a basis or fundamental set for the general solution of the whole D, right? And the general solution is of this form, right? So the general solution, if we wanted to write it down using our same superposition principle, so the general solution is, I'll just write it as y equals, now it can be written in two ways. You can write it as c1 times the first function like this, plus c2 times the second function like that, and that's completely fine. Another way is, since that exponential function is a common factor, you can factor out the e to the alpha x and write it as c1 cosine of beta x plus c2 sine of beta x, right? So now we know what to do if, when we solve our auxiliary equation, if we end up with a complex pair of solutions like this, where we have alpha is the real part and beta is the imaginary part, we can still end up with the general solution of our OLE. So now we have everything covered, and let's go ahead and look at a couple solutions of this, right? So a couple examples of this, I should say, not solutions. So let's look at our first example. And suppose we have y double prime minus 8y prime plus 17y is equal to 0. Right? Well, let's go ahead and, if we write down our auxiliary equation, we have m squared minus 8m plus 17 is equal to 0. And if we check our discriminant, again, because look, when we look at, we can't find factors of 17 that add to give us negative 8 for the clear reason that 17 is a prime number, right? So, but if we check our discriminant, again, if there's any doubts about it, you can always check the discriminant of your quadratic and it will tell you what's going on. So in this case, it's going to be negative 8 squared minus 4 times a times c. So what do we end up with? So we got 64 there minus 68, which is negative 4, and that's less than 0. So this tells me that my roots are going to be complex conjugates. So let's see what they actually are, right? Because what we need to be able to do is to identify the real and the imaginary part of the roots, because that's where I need to use to identify my alpha and beta. All right. Okay, so let's use our quadratic formula now. So it's the negative of this, so it's 8 plus or minus the square root. Now you could go ahead and write this down again, but we already computed it. We computed the b squared minus 4ac. That's how we got the negative 4. That's how we knew that our roots were going to be complex conjugates. So we have negative 4 there, and then at the bottom we have 2 times 1, so that's 2. And so we got 8 plus or minus. Now this is where we end up using this, the square root of negative 1 is I. Because I can write this as root 4 times root negative 1. This is still all over 2. So I end up getting 8 plus or minus 2i all divided by 2. And then in order to identify alpha and beta, I need to write these as, so for instance, I need to write this as 8 over 2 plus or minus 2i over 2. So split this single fraction into two separate fractions, reduce them as much as you can. The real part here reduces to 4, the imaginary part here reduces to 1, and then times I. So I'll write it as 1i. So now we can identify that the 4 is my alpha and the 1 is my beta, right? So once I identify these, then I can write down the, let's see here, I can write down my, so let's see, so y1 is e to the alpha, so 4x times the cosine of beta, so 1x, and then y2 is e to the 4x times the sine of x. So these are your two functions, right? So the basis here, right? So our basis consists of these two functions. So here is our general, oh, let me fix this. So general solution. So our general solution is y equals, well, let me write it, y of x. Since we don't have conditions, we just have our general solution. So y equals c1 times e to the 4x cosine of x plus c2 e to the 4x sine of x. So you could write it like this, or if you'd like to, you can factor out the e to the 4x and get c1 cosine of x plus c2 sine of x. Right, so I think it's extremely remarkable that even though we end up with complex conjugate roots, we're still able to come up with a general solution to this differential equation. All right, let's take a look at another example, and in this example, we'll go ahead and solve an actual initial value problem. So number 2. So let's say we have y double prime minus 4y prime plus 9y is equal to 0. And then we have y of 0 is equal to 0. And then y prime of 0 is equal to negative 8. All right. So let's go ahead and start by writing down the auxiliary equation. So the corresponding quadratic equation is m squared minus 4m plus 9 is equal to 0. And again, we're not going to find factors of 9 that add to give us negative 4. So let's just go ahead and use our quadratic formula. So m is going to be the negative of negative 4, so 4 plus, and then under the square root we're going to have b squared, which is 16, and then minus 4ac. So we have 4 times 1 times 9, and then this is all over 2a. So we got a 2 there. All right, so let's carefully simplify this, see what we end up with. So we have 4 plus or minus. Under the square root, we have 16 minus 36. So that's negative 20, and then that's all over 2. So negative 20, that can be written as, now so first I'll write this as root 20 times root negative 1, again all over 2, and then we'll have 4 plus or minus. Now root 20 breaks down to 2 root 5, and root negative 1, that's our definition for I, and then this is all over 2. So now reducing this, since both coefficients in the numerator are divisible by 2, I'll end up with 2 plus or minus root 5i. Right? And it's completely fine to have a root here. There's no rule that says that alpha and beta have to be integers or even rational numbers, right? So this is our alpha, And this is our beta. So now let's write down what our basis would be. So the basis for all solutions of this differential equation it consists of these two functions, the e to the alpha x cosine of beta root 5x, and then e to the alpha x sine of beta x. Now, once we have our two linearly independent functions, then we can write down the general solution. So our general solution is any function of this form. So what I'm going to do is I'll factor out the e right away. So I'll have e to the 2x, and then in parentheses I'm going to have c1 times the cosine of root 5 times x plus c2 times the sine of root 5 times x. All right, there we go. So now if we want to go ahead and find the particular solution, right, that satisfies these two initial conditions, I do need the derivative, which means I have to find the derivative of this. So it gets a little messy, but having it factored like this is helpful. I just need to apply the product rule once, right? So let's go ahead and do that. I'm going to scroll a little bit over here, give myself a lot of room, see how much of it I actually need. So y prime. So the derivative of the first is 2e to the 2x, and then times the second, so I'll just bring down everything that's in the parentheses. Right, like that. And then plus the first, which is this, e to the 2x times, and then now the quantity, well, I have to differentiate what's inside, so I'm going to have to use the chain rule here and the chain rule here. So when I differentiate cosine, I'm going to get negative sine, but then I'm going to have to multiply by the derivative of the inner. So I end up getting this, negative root 5 c1 sine of root 5x. And similarly, when I differentiate sine, I'm going to get cosine, but again I have to multiply by the derivative of the inner. So I'll have root 5 c2 cosine of root 5x. So that's my first derivative. Now let's go ahead and apply the condition. So I'm going to start with this one and say, well, what do I get knowing that when x is equal to 0, y is equal to 0? So let's write that down here. So when x is equal to 0, y is equal to 0. So I'll put a 0 there for y. E to the 0 we know is 1. And then the quantity, the cosine of 0 is 1, so I have c1 there. And then the sine of 0 is 0, so it eliminates the c2, so it ends up like this. So this just tells me that c1 is equal to 0. Well, that helps. Why does that help? Because now when I go to use the second derivative, the first derivative, in order to use the second initial condition, wherever there's a c1, I'll be able to replace it with 0, right? So this is saying that when x is equal to 0, y prime is equal to negative 8. So let's do that. I'll just do it below here. So when x is equal to 0, y prime is negative 8. So I'll have a negative 8 there. And then let's just go through and just substitute everything that we know, right? So this out here becomes 2. C1 I know is 0, so it's going to eliminate that term. I don't know what C2 is, but I know the sine of 0 is still 0, so that term is 0. So far, you know, that's all of this is eliminated, and then we just keep going. Plus, e to the 0 is 1. In the parentheses now, again, C1 is equal to 0, and I know the sign of 0 is 0, so it's like doubly 0 right here. And then this is where we get our first non-zero term. The cosine of 0 is 1, and I don't know what C2 is. So then I have plus root 5 C2 like this, right? And then I have to solve this equation for C2. Well, it certainly helps if we simplify this. So I have negative 8. And so then this is 0. And then in parentheses, I have the square root of 5 times C2. But that's times 1. So it's still just the square root of 5 times C2. So therefore, C2 is negative 8 over the square root of 5. So I now know what the particular solution is, and let's write it down. So in fact, I can go back here now and say that our particular solution is y of x. So we'll have the e there, so we'll have e to the 2x. Remember, C1 came out to be 0, so that whole term is eliminated. And then we'll have the plus, and then C2 is negative 8 over root 5, and then times the sine of root 5, oh, not root x. The x is not under the root, that's for sure. That's a whole other situation. So we end up having root 5 times x. So then this simplifies to, I'll put the coefficient first, the negative 8 over the square root of 5. Then I'll put the e, and then I'll put the sine function. So here's our particular solution to this initial value problem, right? And there you have it. So with the power of Euler's identity, even though we end up with complex roots, like we did right here, right? We're still able to generate a basis that consists of real functions that are guaranteed to satisfy our differential equation. Really powerful stuff, very useful. Hopefully you found it interesting. I certainly enjoyed presenting it to you, so much so that I'm going to find other math to present to you in the next video. So please join me then. See you then. Bye.